This is Chapter 8, Summary Notes on Gases, and this particular video involves Charles's Law. All right, you see a picture of a couple of pistons over here on the left involving volume and temperature. And we know that all gas laws are derived from the ideal gas law, which is PV equals nRT. All right, in this instance, we're keeping the pressure and the number of moles constant. All right, and R is a constant that we'll talk about in another video. So we're varying volume and temperature. All right, and you can see the working relationship on the side, which is V1 over T1 equals V2 over T2. And over on the calculator display, I've put in the variable substitutions that are shown for the pistons. And we see that when V1 is divided by T1 in this instant, we get 0.005. And the same thing is true for the other one. If we put 2 in divided by 400, we get 0.005. Now, just to make sure you understand how both conditions can equal the same answer, let's flip the equation. Let's say T1 over V1 equals T2 over V2. All right, well, that's the next set of lines that's on the calculator display over here. 200 divided by 1 gets me back 200. 400 divided by 2 gets me back 200. Yes, these numbers are very different, but they're a constant regardless of which formula that you use, which means that you can flip these formulas to suit what you need to solve for. So in this next question, it says solve Charles's law expression for T2. All right, so let's take T2. All right, we can see that up here. And we know that if we flip the equation, all right, I'll rewrite the equation. All right, we want to solve it for T2. This makes V2 come over to the right-hand side. We can do V2 over 1 multiplied by the inverse of what we want to get rid of. All right, I hope you remember that from your math. All right, and then we get the V2 T1 over V1 equals T2. All right, do you need to memorize all of these? No, please don't. If you remember your ideal gas law, and you can derive any other gas law from that, okay? Because the other terms drop out that are constant. All right, the terms that are constant in this case are the R, the N, and the P. And to get the V on the one side, because this is the one set of conditions, so you can think of this as T1 and V1. All right, so we got V1 over T1. All right, and remember, we're setting that equal to another set of conditions, so we can make a prediction if we know 3 out of 4 of the variables. All right, so let's try that. All right, here's a balloon. We have a lot of balloons in this chapter. All right, we have a balloon. Let's assign some variables, but let me make some room before I do that. Okay. And just want to move it over a little bit. All right, so V1, all right, our volume is going to be in black. Well, hopefully we'll be a little consistent there. 785 mLs. We want to assign the variables as we go. Temperature, we'll put that in red, equals 21 degrees Celsius. Automatically add 273 to that. Okay? All right, we're looking for the new volume. And it says, what is the new volume if the temperature drops to 0 degrees? All right, now you can see right now, if I have 0 degrees in there, and I'm dividing, I'm going to get 0 as an answer. So remember to change it to Kelvin. All right, so we have 273 Kelvin for T2, and we have 294 for T1. All right, so now we can just substitute what we need to do. All right, 785 times T2, which is 273 Kelvin, over 294 Kelvin. And again, you can make a prediction. All right, if this is a direct relationship, if temperature is going down, all right, which it is from 294 to 273, temperature is going down. All right, volume must also go down. All right, so we'll make that prediction. And I think you can see that because 273 over 294 will be less than 1. All right, so coming over here to the calculator, 785 times 273 divided by 294. All right, so we get 728. Point 9. All right, and then this will round to 729. And it's milliliters. Okay, equals our V2. So did it go down? Yes, it did. It went from 785 to 729. So it went down. All right, box in your answer. All right, so here's another question that you can try. All right, so stop the video and then come back and check your solution and your answer. All right, if you look at your screen, let's check your assignment of variables. The first volume is 420 milliliters. The second volume is 640 mLs, so it's increasing. So since this is a direct relationship, volume increases because temperature probably increased in order to do that. All right, so I'm making a prediction about the second temperature, which is what they're asking you to find. I'm going to say that the temperature is going to increase because the volume increased. The other thing in this problem is that they give us the temperature in degrees Celsius. So did you remember to add 273 to that first temperature to get 291? All right, and again, we're solving for the second temperature, and we're solving for it in degrees Celsius. But we can solve for the Kelvin first and then change it back. All right, did you remember to flip your formula to make your isolating a variable a little easier? All right, so if T1 is over V1, T2 is over V2, I can simply multiply both sides by V2 to cancel it on the left side. And I'll just cross that out on the left side, if it will let me do that. All right, and brings it up to the position up top on the first set of by the first set of conditions. All right, so then I plug in my numbers, and I can see from the relationship here that 640 over 420 is much greater than 1, so the Kelvin temperature will go up, and it does go up to 443.4. I always keep one more decimal place than my significant figures. I'm subtracting 273 from that, and my final answer is that 170 degrees Celsius. And did the temperature go up? Yes, the Celsius temperature started out at 18, and now it's 170, almost a tenfold increase in temperature. All right, but that's on the Celsius scale. It's only a little less than doubling on the other scale. All right, so here's some conceptual questions to think about. It says use the gas laws to complete these statements. All right, so we can think about the kinetic molecular theory as we look at these. All right, when pressure does what? The volume decreases at constant temperature and moles. This is Boyle's law. All right, so when pressure increases, all right, it's pushing more molecules in a smaller space, and those straight line pressures are hitting the walls of the container, increasing the pressure. All right, when temperature goes down, volume will also go down, okay, at constant temperature and pressure. This is Charles's law. It's a direct relationship. Okay, and the molecules are slowing down, so they're going to take up less space. All right, that has to do with your velocities. All right, and number 3, if pressure is decreasing when volume changes from 12 to 24, okay, because the volume is expanding and the molecules are slowing down somewhat, so the pressure is decreasing. Again, that's Boyle's law. That's an inverse relationship. And then lastly, if the temperature is increasing, look at that infold. Remember though, don't think about it as tripling here, because you always need to think in terms of your Kelvin temperature. So if we add 273 to each of these numbers, it's definitely not a tripling that's going on here. All right, this is 288 Kelvin, and over here it's 318 Kelvin. So it's going up a little bit, but it's certainly not tripling. All right, but the volume still is increasing when the temperature changes, okay? So as the temperature gets warmer, the molecules are going to be moving faster, and if you're at constant pressure in moles, the volume has to expand to accommodate that increase in temperature. And again, that's Charles's law. Okay, so Charles's law involves pressure, volume, and temperature. Boyle's law involves the pressure and volume. One is inverse, and the other is a direct relationship. All right, next video will be on Charles's law. Gay-Lussac's law. We just did Charles.